Okay, and welcome to lesson 6 on tension force, example 3-2, or in your books, 3b, the second part of example 3. Okay, so in this example, we're going to be looking at this, our similar situation similar to Atwood's pulley, which is described at the top of your page. And I'm just going to be rolling through this with maybe more of an old school strategy. I don't think that it's super beneficial to be memorizing formulas, especially formulas that aren't given to you on your formula sheet. Being able to reason out the direction that forces are pulling and combining masses and finding net force is a lot more beneficial in the long run. You can solve any problem with the skills, whereas you can only solve very specific problems with these formulas that are given to you. So let's go about this by figuring out where our forces are in this problem. Okay. We have, before we get going, our diagram. We have sort of a pillar here, and on this pillar there is a 10 kilo mass, and to either side of it there are masses hanging from a pulley. All right, now I think we can tell probably right away that since this 7 kilo mass is heavier, that the system is going to be pulled to the right. Right? The question though is, what's the acceleration on the system? So sure, we can see right away that this is going to be pulled to the right. The question is, how quickly or what rate is this going to be increasing its speed at? Okay, well, I'm going to, before I jump into any formulas or anything, sketch in my two forces. We're going to have one force of gravity here and one force of gravity here. Okay, and so we can say maybe this is FG1 and this is FG2. Cool. Well, where do we go from here? We always have our standard FNet formulas, so let's just go with those. We can say our FNet is equal to mass times acceleration, and we're looking for acceleration, so let's say that acceleration is equal to FNet over mass. Alright, well, we've seen things like this already before. Our FNet in this case is equal to well, I'll write that up here. FNet is equal to FG1 plus FG2. Right, and then FNet is equal to FG1. Now FG1, they're both pulling down, but if we think of like this middle platform as our horizontal value that is going to be representing our direction, FG1 is pulling this thing right out to the left. Its direction just gets changed by the pulley. So I'm going to say FG1 is going to be our negative direction. So this is going to be negative, well, maybe mass times negative acceleration, or as I say, it's negative mg plus, because our FG2 is going to be pulling this to the right, plus mg, and maybe I'll put m1, m2 in here. So we can solve a numerical value for this. FNet is equal to negative 4 times, I'm going to run a little short on space here, 9.81 plus, I'll just drop it down to the next line, 7 times 9.81. Okay, so our net force on this system is going to equal. Oh dear, I didn't actually calculate that myself. I did more steps in one here. So let's go 7 times 9.81 and subtract 4 times 9.81. Alright, so I get a net force of 29.43 newtons. Okay. So with that said, we can do acceleration is equal to 29.43 newtons over, that's not very nice, over the total mass given here for our whole system. So 10 plus 4 plus 7. These are all in kilos. Okay, so our acceleration works out to 1.40. We are only given 2 sig digs, so 1.4 meters per second squared. That's a positive value. We were keeping track of all our positives and negatives here. Right, this was our negative value because it's going to the left. So we can say that, as predicted, this is moving to the right. And there we go. That is our final answer.